Okay. All right. Oh wow, Crow is here. Kappa, how's it going? Wow, good job, Crow. Way to wake up. Oh, great. Kappa! Wow! Wow, everything you do today is just like incredible. Oh, and what are you doing here? Okay, Anonymous. Hope your semester is going well. Hey, why isn't this recognizing Anonymous? I'll just do this. Yeah! Alright. Okay, thanks Kappa. Thank you. Thank you for that. Oh, wonderful. That's wonderful. Good to hear. Ah.
Yes, science!
Hey, SciPet, how's it going? Hey, well, that's good to know. Good to know. Wonderful. Hi. Wait a second. JuneQS. Do I know you, JuneQ? Do I know you? I recognize the name. Okay, awesome, Psypet. It's good to be awake. Alright, let's start the boring streamer music in the background. Oh, it's not even up. Let's see. What is it? What is the Spotify? That's what it is. That's the particular program that I have to click on. Let's click on it. This music. Here we go. So JuneQ. Recognize that name. Okay. So, class, as usual, I can only do 3 things every day, basically. Today we're basically transitioning into chapter 10. And chapter 10 is one of the basically 2 or 3 chapters that builds the little building blocks of the proof of the Galois correspondence, fundamental theorem of Galois theory. Okay? And so first I'll begin by telling you that separability is not going to play a big role when you have a characteristic 0 field. Okay, that's going to be quite clear. So it's not really going to affect us much in this class. It's also not going to affect us when we talk about finite fields, because for mysterious reasons. Okay, then we move to the main point of chapter 10. I'll state the main point of the chapter, and we'll begin by at least stating a little tiny scalpel-like tool due to Dedekind that is crucial in the proof of that main claim. All right, let's do that. All right, let's begin. Separable, fine. No problem in characteristic 0. Okay, so how does this work? You have an irreducible polynomial. And look, you write it out. Look. Oh, look at it. Wow. Look, see? Over some field K. Okay? Let's say the field... okay, let's just... Don't introduce the characteristic yet. Separable. Irreducible polynomial. And it's separable, right? If it has n distinct roots. In right now our fields live in an ambient world called C, but in general it's just inside the what's called the algebraic closure of K. Okay, that's what separable means. But we also saw algebraically what it means is when you do derivative polynomial, it means that f of x and its derivative, notice that the derivative is still a polynomial over K, curiously. Do not share a root. A complex root, okay? Now, if f is irreducible, and we're over a characteristic 0 field, which is true if you're a subfield of C, f of x and f prime of x will absolutely not share a complex root. But That's because the degree of f prime of x is exactly 1 less than the degree of f. In particular, f prime of x is not the 0 polynomial. In particular, why? Focus on the top coefficient. The power rule makes this into this when you take the derivative. And if a sub n was not 0, then n times a sub n will also not be 0. Characteristic 0 field. N is not secretly 0. That's where it comes in, right there. So the derivative is a smaller degree polynomial. It's not the 0 polynomial. But then how can these two share a root? F of x was irreducible. And so if you take a root, f of x was its minimal polynomial. F of x is the minimal polynomial of any one of its roots. And so f prime of x would be a smaller degree polynomial having the same root. That violates minimal polynomialness. Okay, so this violates irreducibility of f of x. F of x is a minimal polynomial for one of its roots, any one of its roots, all of them at once. Okay, so that's why when you take in characteristic 0, separability doesn't play a role. You can't have the derivative of the polynomial and the polynomial share a root. Notice how it's very important that we start with an irreducible polynomial. Of course, reducible polynomials can have repeated roots. Of course, that's stupid. But it's all about whether irreducible polynomials have repeated roots or not. And in characteristic 0, that doesn't happen. So, where will this separability show up in the proof of the Galois correspondence? I'll tell you exactly where it shows up. So look out for separability here. Look out for separability in sentences that go like this. Something. M is degree n, irreducible polynomial. So it has n distinct roots. And then they'll call them something. And then they'll go on with the argument. Right there. Whenever they say that a degree n irreducible polynomial has n distinct roots in some counting type argument, that's where the separability condition is coming in. So it's a little subtle point, but it's in those kinds of counting arguments, saying that there are n distinct numbers and now I'll use that to count something. The word distinct is where the separability condition will sneak in. All right, so that's coming in the next week or so. Okay, so let's move on. Move on to chapter 10. Okay, what's the point of chapter 10? So here's the setup of chapter 10. You have a field. Abstract. Chapter 10 is super universal. It's like true at the level of like fabric of reality, fabric of our universe. Okay? It's like no hypotheses, barely any. All right? It's like fundamental physics.
Yes, science.
All right? Good. Okay, Kappa. Your teacher's pet, but and that's a good comment you made. So, K is just a field, any field, and G is a group, a finite group of automorphisms of that field, period. When we say automorphisms, it's field automorphisms. Then, of course, you can create the fixed field of that group. And I'm going to write it as K upperscript G, or fixed field. It's the set of elements such that G of K equals K for all elements in the group. Stuff that's fixed by it. It's clearly a field. Just go ahead and sums of these stay fixed, products stay fixed, divisions stay fixed, inverses are unique, so they stay fixed. Okay? So this is a fixed field. So you have a field, a group of automorphisms on it, a finite group, and then therefore you get a subfield called KG, fixed subfield. And the point of chapter 10 is to tell you the distance from K down to KG. How small is the subfield, the fixed field? Chapter 10 addresses the following question. How small? Relative to K. And we have our notion of size of one field over another. It's the degree. That's what we're asking. And here's the answer, the ultimate answer that chapter 10 gives. The degree of this field extension is the size of the group. Very clean statement. Very clean. It's as big as the group is. Fantastic, wonderful, clean, universal statement. Amazing. All right, so that's what we're going to learn in chapter 10. Any questions about this statement? Good. Go ahead and ask any questions whenever you want. All right, so what we're going to do is introduce what's the codomain of elements of G. G is automorphisms of the field K. So G is the set of, G is a collection. So what's an automorphism? An automorphism is a map from K back into itself, which is a, which has an inverse field homomorphism. It's an invertible, so it's a bijective field homomorphism. Yes. Procrastination. Okay, good. Yes, isomorphism from kappa to kappa, as RDL says. Yes. Okay. Scramblings of this field, but they're not random permutations. Yeah, they respect the field operations. Very, very big constraint. Okay? Very big constraint. Hard to make. Okay. Good. Right, no, just automorph. The word automorphisms is like, auto means like self. Self scrambles. Okay? Good. All right. So, now, that's the goal. It's a very general, super general fact. It doesn't have to do with subfields of C necessarily. It's just very, very general type of fact. Okay. Linear. So the key little scalpel that is very, very effective and shows up in different forms. Similar kinds of facts show up in different forms in different algebraic classes. Classes meaning, like school classes. Okay, subjects. It's an example of linear independence of blank. This type of argument shows up many places. You've seen it once probably in a linear algebra class. So we're going to prove a little algebraic device called linear independence of monomorphisms. And this is due to Dedekind. Dedekind realized the importance of these kinds of little devices probably earliest among all algebraists, and exploited them very successfully. Okay, so here's the setting. We're going to linear independence of field monomorphisms. Yes, he used the scalpel to cut things. Actually, no, he didn't really do. He didn't use this scalpel for cutting, actually. Okay. That's pretty good. Okay, so here's the setting. Say you have a field, and then another field. Two fields. And suppose you start studying the ways in which K kind of visits L. We use field homomorphisms to transfer one field to another. So suppose we study field homomorphisms from K to L. We're going to look at the set of field homomorphisms. Now remember, a homomorphism of rings where the domain is a field, it's always injective. So that's why the book is always using the word monomorphisms. It's just emphasizing that, hey, these are injective maps. These are one-to-one, always. Okay? This is automatically one-to-one. Okay, so it's like, really, you're studying the ways of embedding K into the target field L. That's what this set represents. It's just a set of ways of doing that. And now, the linear independence of field monomorphisms theorem states the following. Any finite subset of such visitations, such monomorphisms, are linearly independent over L. Let me state it like this. Distinct monomorphisms then linearly independent they're linearly independent over L, the target larger field, right? What does this mean? Meaning there are no non-zero. So I'm going to use the word non-zero. Okay, let me say it like this. There is no non-zero tuple A1 up to AN of numbers in L such that A1 lambda 1 of an element for all elements in the field K. Okay, so mean lambda 1, lambda 2, lambda n. It's a rather remarkable thing. It's saying if you choose distinct ways of embedding K into L, there's no way of combining them using coefficients in L to get the zero function from K to L. There's no way of combining them to get a zero. I want to emphasize, if you take two field homomorphisms and you add them, meaning create the map that just adds outputs, that's not a field homomorphism again. That's just a complete garbage map. Okay, it's not a map that doesn't have any good structure. All right, so it's not obvious that you can't just say, well, 0 is never a homomorphism of fields, so of course this is not going to be true. No. We're taking homomorphisms and then we're like scaling and adding them, getting completely outside the realm of field homomorphisms now. They're just functions. Okay, so that's how you parse the statement. This is what it means for these functions to be linearly independent over capital L. It means that there's no capital L way of combining them, which becomes identically the zero function. Okay, that's the theorem of just a group under composition, not addition. Yeah. Oh yeah. Exactly. No. Yeah. It's addition is very, very tragic, and scaling too. Scaling ruins homomorphism because the element 1 has to go to 1. Yeah. K need not be L. That's right. K need not be L. Absolutely. Good point. Even, yeah, there's no notion of composition here as well. Exactly right. Procrastination. 100%. This is a very abstract setting. Just our field and the field we're visiting. The sort of larger field that we're visiting. It's larger because we are mapping to it, therefore injecting into it. That's why it has to be necessarily, quote, larger. Okay, good. Great. So, the proof of this thing so we're talking about linear independence, but big lambda is not necessarily a vector space in any way, shape, or form. If you think of big lambda as this set, absolutely, this is just a set. There is really very little structure to this set. Sort of. Okay? It's just a set. It's not obvious. It's not like automatically a K vector space or an L vector space. No. Okay? Yeah. Awesome. Good. So, and typically in life, actually, I mean, in all of our lives, this will be a finite set. Good. Awesome. Wow, Smash Time. What a contribution. No kappa. No. Very little relationship between those two. In fact, typically for us, if lambda K to L is non-empty, then lambda L to K will be empty. It will be very, very difficult, typically, to have backwards homomorphisms from the large field back to the small field. Typically, for us. That's right. So there's no real duality happening here. Exactly. Okay, it's because if you have a small dimensional vector space mapping to a large one, that can happen in an injective way, of course. But if you have a larger dimensional vector space mapping back to a small one, it'll never be an injective map. and field homomorphisms must always be injective. It's a very strong condition to be a field homomorphism, extremely strong. And in fact, the homomorphism structure, the fact that you're respecting in particular multiplication, will play a huge part in this in the proof of this linear independence of monomorphisms. Okay, so what we're going to do is look at just following the book, because it's excellently exposed there. Look at the first two cases of this thing. Like, what if you took two different visitations from K into L? All right? Yeah, basically, or if you're in an infinite dimensional situation, infinite degree field extension type fields, then you can get, because infinity can map into itself non-trivially and so on. So yeah, visitation, when one field visits another. Yeah, it's something I just think about. It's the way I think about this situation. K is manifesting in L according to this first field homomorphism, and suppose you have a second one. Two distinct field homomorphisms. Okay, distinct field homomorphisms. What does it mean to say that these two are independent over L? It means it means that one of these functions, just input output functions, is not obtained by the other function times an element in L. Okay? It means that there is no, either this way or the other, there is no necessarily non-zero element such that lambda 1 is a times lambda 2 as functions, meaning, i.e., lambda 1 applied to any element is a times lambda 2 applied to the element for all elements in the domain field. Okay, that's what it means to say that lambda 1 and lambda 2 are independent. It means there is no element. Okay, great. Yeah. Yes, exactly. Okay, so for this one, you can use, for example, that 1 has to go to 1 under a field homomorphism. So let's follow Smash Time's observation. So plug it in here. Plug it in. You get 1 equals a times 1. But then hold on, a has to be the element 1 in capital L. But wait, that means that lambda 1 of x equals lambda 2 of x for all x. Meaning lambda 1 and lambda 2 were not distinct homomorphisms. Okay? Just that small bit of observation, thanks to Smash Time, clinches this version. Any two distinct homomorphisms cannot differ by a scalar in L. Let's summarize it like that. Okay, now let's do 3. Let's do 3 now. Let's do 3. Try n equals 3. Just for fun. Okay, so now try n equals 3. Now you have 3 distinct homomorphisms. Three visitations. Okay, the claim is there are no 3 non-zero elements, A1, A2, A3, that combine these to give the zero function. Not all Zorro. For some reason I wrote Zorro. Not all Zorro. Such that. Okay, as functions. Alright, meaning. Okay? Okay, first observation. First observation. We can assume that all 3 of A1, A2, and A3 are non-zero. Because if any one of them is 0, it reduces to the previous case. And so you're starting to see the inductive structure that is in the proof of the actual main thing. If one of these AIs is 0, you're back in the previous case, right? So you can assume all AI are non-zero. Okay, and now here's the trick. The trick is lovely. Lovely trick. And this, no doubt, is Dedekind's trick. Okay. This is true for all x in K. But now, replace x with x times y, where y is some arbitrary element in K. It's true for x squared? Oh, that might be, is that an even more clever way to do it? Maybe it is. Maybe it is. Is this some kind of Wronskian proof? I don't know. Tell me whether this is what you mean by a Wronskian proof. It's a type of trick that happens in 3 or 4 places in early algebra subjects. It's almost like linear independence of eigenvectors for different eigenvalues. It's almost, it's in the same line of trick as that. Okay, you can also probably use a Vandermonde determinant for it. I think I see what you're saying. Yeah, you probably could do it like that too. Okay, so here's a lovely trick. Replace x with x times y everywhere. It's also a trick you see in manipulation of Gauss sums. You've seen that? Anyway, so replace x with x times y. Notice we're gonna very importantly, crucially, use field homomorphism structure. They're not just random maps, lambda. Field homomorphism. Because if you replace x with x times y, you get this. Now I'm gonna have to use my full PhD here to do this correctly. So we know that we're pretending this is 0. And now, wow, look, they separate because lambda i's respect the multiplication structure. Oh, what happened? Incredible. Oh, thank you, Dolphin Whale, for following. Okay. So, we also get this new identity. Okay. And now what you do is you compare the two relations. So these three things are the same. Yes, you can. Yeah. Please enter arbitrary. Yes, please. Thank you. Such polite student. Now these three are the same. So and y is like arbitrary. Y is an arbitrary element in K. Okay, and so now the claim is the only way you get both of these identities to hold is if lambda 1 of y equals lambda 2 of y equals lambda 3 of y. That's the ultimate claim here. Okay, so the only way you can get these two to be simultaneously 0 is when those things happen. Okay, so how would you actually do it? You would do something like row reduction. You would do row reduction. Okay, so you do row reduction. You multiply equation number 1 by lambda 1y and subtract equation number 2. And what do you get? What do you get? You get A2 lambda 1y please check. There's too many indices. I can't concentrate. Okay, A3 lambda 1 y. Wow, my PhD is starting to wear thin here. Okay, A3. Yes, I think it's happening. Yes, good. Wow. Now, what do you notice about the first entry? This is an amazing number. Amazing number. It's an amazing universal constant. Constant of nature. It's one of the most important constants in science.
Yes, science!
Okay? That's 0. And now what we have is a relation between lambda 2 and lambda 3 is a relation of smaller length, only 2 coefficients. But we already know that lambda 2 and lambda 3 are linearly independent by a previous case. So we conclude by basically induction, right? Or previous case, that A2 lambda 1y minus A2 lambda 2y equals 0, for example. That this coefficient has to be 0 for all y. And A2 was a non-zero number, so you can cancel it out. And you get that lambda 1 was lambda 2 as functions. And that's bad. Which is good. Okay. This is the proof. Oh, we did it for n equals 3? No. We did it for n equals n. You just have to squint at it and set up the inductive argument yourself. Okay? So the case n equals 3 contains the idea of the inductive step. Does that make sense? You row reduce after applying x times y substitution. This kind of trick of exploiting the extra structure that these functions obey by like basically substituting a product into the entries is used at a couple 4 or 5 choice locations you'll find in your algebraic classes moving forward. Okay, and I just wanted to give it its time of day at this moment. All right, so distinct visitations are linearly independent over L. Fantastic. Okay, great. So it's 10:11. What I'm going to state now is basically I'm just going to say some obvious things to end class with. Obvious in the sense of wait, where did my chat go? Is my chat here? Yeah. No, where did it go? Okay, I'm now going to finish class with some very obvious linear algebra statements. But I want to emphasize that they are universal, very abstract. And then we will be very easily able to prove the main point of chapter 10. How far is the fixed field from the original field? It's order of g far away. Okay? That we will finish on Monday. It's very simple. But last quick thing. It's about linear algebra over an arbitrary field. Suppose you have a system of equations with more variables than equations. I'm going to write some system of equations, all right? L1 system of linear equations. If you got a system of hey, how's it going, Skughead? How are you doing? K linear equations, meaning coefficients are in K, and the xi's are just variables, and you're trying to find elements x1 in K, x2 in K, xn in K that solve it. Okay, suppose you have a system of K linear equations where m is strictly less than the number of variables. Equations less than variables. Then there is a non-zero solution. Non-zero means not all of the xi's are the zero element in K. Some of them might be zero, but not all of them. Solution vector. Why? Why is this true? I'm just going to tell you why. It's because row reduction didn't need your favorite field R or C or whatever. All it needed was the ability to write down K inverse and scale one coefficient to match another and then subtract. It was all the linear algebra that came out of row reduction is universal. It is part of the fabric of the cosmos. All right? Okay.
Yes,
That didn't work
science.
very well. Okay. So why row reduction argument still works? Row reduction of the m by n matrix argument still works. Okay? So that's all I want to bring to your attention. That this more variables in a linear equations than unknowns always produces non-trivial solutions. That principle will be used in conjunction with linear independence of monomorphisms, Dedekind's result. We'll use them together to get our main objective of chapter 10. Chapter 10, I want you to think of as part of the refined understanding of how the Galois group's size relates to the degree of the field extension that you're studying. That's part of it's. We're still in sentence number 2 of Galois theory. Fantastic. Okay, so questions, comments, credits. Who's here? Oh, Kappa. Kappa and Smash. Thank you for reminding us that lambda of 1 equals 1. That was incredible. Hey, wow. Look who it is. Look who showed up. What? Galois group itself has shown up. This means we're close, class. This means that we are very close to establishing the Galois correspondence. We're like a week away, basically. I mean, it's like Groundhog's Day. If Galois group shows up, that means you're close. Okay? Awesome. BM Pog. BM Pog. BM Pog. Please use the emotes correctly. Good. Thank you. Oh, Arbitrary is here. Speaking of which. So polite. All right, now who are the non-mods? Femvox, I see you in there. I see you. You showed up. Crow showed up to class, but then went back to sleep, probably. Or this is all beyond him. So, Skugget. Welcome. Haven't seen you in a while. How are you doing? Galois group. Wow, amazing. It's an honor. True honor. It's a true honor to have you here. Do you stream? Do you stream Galois groups? Do you exhibit them on stream? Ah, you want a recorder? Why does the Galois correspondence? Why do Galois correspondences show up outside of field theory? It's probably not fair to call them Galois correspondences. Meaning, it's usually a structure that a correspondent that inverts like a poset and matches them kind of on two sides. That's that general situation where you have two sides of a story and one side is kind of in reverse corresponding to the other by a functor. Yeah, that whole situation is typically called a Galois correspondence. But it's not that the situation is like equal to, there's some secret fields in the background, fields in the sense of algebra, that are explaining it necessarily. But the general backwards situation, functor equivalence, is called Galois correspondence. Yeah, it's just because this is the first one that people fully kind of wrote the details out for and witnessed. We had a joke in university that when few students of our faculty meeting, they form Galois group. Lol and then command or backslash. Yeah, Skugget, it's yeah. Oh, you're physicists. Yeah, scream some physics. Absolutely. Hey, Vixen. Oh, Vixen is here. Hey, don't forget Vixen. Don't forget. All right. Thank you, Smash Time, for that. That was important. Right, group theory, absolutely. Yep. I've heard that it's very important in physics. Hey, all my students, RDL was here. I saw you. Pet. Start reading over the weekend, maybe, just for fun. Chapter 10. Chapter 10 time. I've gotten you basically to the halfway mark of chapter 10. All right, we'll zip through its conclusion on Monday and start chapter 11. So next week will be 10 and 11 all at once. Very good. And so we'll be right around the corner from establishing the Galois correspondence. Awesome. Great. Who else did I forget? JunQ. JunQS. Now, I swear. I think I know you. Okay. Well, I guess... Oh, recorder. Sorry. Let me play you... Smash Time really enjoys classical music, so... Here we go. Thank you, Arbitrary. Thank you. Thank you for the support. Thank you, Skugget. Thank you. Last part was a little bit rough. Okay, folks. I need to learn. Actually, I have a bunch of the... Oh, yeah, folks. There's some news in my life. Due to events that I don't want to talk about, I have to take over an abandoned Calculus 3 class. not abandoned, but unfortunately the professor cannot continue with the class, and so I'm taking it over mid-semester. Calc 3. Oh, Vixen, I can't go into details too much, but there was a medical incident that happened. The professor is fine now, recovering, but someone has to take over their class for the rest of the semester, and I decided to do it. But it's like in the middle of the semester, I'm just taking over a Calc 3 class, so I need to figure out how that's gonna go. Oh, Vixen, that's not Vixen. It wasn't like that. Whatever that happened, it wasn't like that. It was just nature kind of intervened, and anyway. So I have to and this poor class has been, and remember there was a crazy winter storm. You guys remember this? Maybe you guys are not in the zone. Yeah, Vixen, maybe. See, the thing is, what I don't want to do is completely, the class has already gone through several several changes and issues. Like that storm basically knocked out a week of engagement. It's an online class, and so I don't know whether I should tell them, hey, you know, I do things differently. There's this thing called BMP Twitch channel. Let's go do the rest of the class over there. Because it's just one more crazy change for them. The class has already gone through a lot. So I don't know. Maybe I'll ask them if they want that. But in any case, it's gonna eat up a lot of my time because I kind of have to maintain some kind of continuity with how they've already been doing things. So that's gonna be a time sink. Yeah, Green's theorem and Stokes. We get to Green's. We're supposed to hit Green's theorem, but not Stokes. Stokes is in the advanced calculus class. There's a class called advanced calculus or something. So we don't hit Stokes, we hit Green's. Yeah. So, in my opinion, actually, going through all of, like, it starts with vector calculus and then all the integration and arc length and all this stuff. It's really hard actually to pack in all of the versions of course, Stokes' theorem, the low dimensional versions, in a way where it's not just completely like packed in at the last minute. In my experience with Calc 3. So I'm not sure how much people actually digest in that very last week or so of those kinds of Calc 3s that pack all three versions of Stokes, low dimensional Stokes. Yes, exactly, Skugget, exactly. And I actually believe that those last three versions of Stokes deserve way longer meditation, because there's some ultimately simple ideas that can be explained thoroughly, that sort of show that these are one manifestation of one simple idea. And you can show the applications and talk about, you know, balls of electricity or whatever that physics people use one version of Stokes' theorem for. It requires more time, I feel. That last bit. So yeah, I think it's a good idea to end on greens and do greens somewhat more in depth, or just without rushing it through and going to higher dimensional things, and kind of separating it out for a different class. On the other hand, it's for a wider audience, so when these students go to physics class, they use some Gauss's law of this or that, it might be a little bit jarring if they haven't seen it in a math class first. So it's a trade-off. I don't get. It's not easy to just say let's stop at greens, but that's. I mean, practically, that's as far. With my pace, that's where I end up stopping. Yeah, like the product rule, you mean? Is that what you mean? Yeah. Like the, sorry, integration by parts, or I don't know what Leibniz integral rule mean. But no, but I haven't taught the next class, so there is no Stokes anywhere. I mean, I can just give some lectures on Stokes, but I don't. When would I do that? It's sort of just kind of random. Oh, okay, Kappa. That, yeah, product rule. Way less time for sure, but I'll try to get back on that. But Vixen, that thing is also going to be replaced by a different request, which was to run this BMP After Dark seminar. That's going to start soon-ish. Like, within the next 2 weeks. BMP After Dark. I mean, you guys named this. It's intersection theory. The worldwide intersection theory. Intersection theory seminar. It's for my student and former student who's in Australia, and he wants to learn intersection theory. And there's a bunch of people that he knows that might be interested over there, and a couple others in other parts of the world. So intersection theory seminar. That'll go for a while. Who knows when that will end? Who knows when it will, what'll happen to it? But it's for mature audiences. It's rated X. Your X is an algebraic smooth projective variety. Okay. Yeah. Melbourne. Procrastination. Hey, Gath. What? Gath is here. Yeah. Who's in charge of the shout outs around here? Kappa? What are you doing? Gath teaches. Okay. Gath teaches like everything chemistry. I don't know what exact type of chemistry she's teaching this time. It's some organic crazy stuff. But every time she leaks her Canvas page on Twitch, I have a heart attack. I'm like, what? Like, what is this? Perfect. It's like better than Khan Academy. Way better. I don't get it. Yeah, Kappa, what's going on, man? What's going on? Good. Okay, I pressed the wrong button. That was elegant. That was elegant. I just changed it to underline. That's really cool. I can't believe I did that. That was really cool. Wow. Yeah. Yeah, it's pretty good. Hey, oh, and Burroughs is here. What? Celebrities. Also, chemistry master. Teaches chemistry. Maybe teaches or office hours. One of the two. On here, Twitch. Science and tech. These are like the pillars of science and tech, folks. They all, I mean, of course they frequent this here stream. I mean, this stream is the hub of science and tech. One might argue. So. Wait, really? Procrastination? That's where you went? Oh, Melbourne. That's cool. Yeah. Yeah. Awesome. Oh, fantastic. That's really cool. Yeah, so there's some grad students there that are wanting to learn the algebraic geometry in the realm of intersection theory. So, which is a hard topic, but a beautiful one, and simultaneously concrete and deep. It's a good mix of easy to state questions whose answers involve some of the whose explanations involve facing some of the more challenging bits of intimidating parts of algebraic geometry. Excited about some parts of Calc 3? Sure. I'm more excited this time about trying to make the transition, trying to salvage the class. I mean, of course, nothing against what happened before. It's no one's fault that the class has been under such has gone through turbulence, but try to turn it around. I mean, Calc 3, you're kind of on autopilot when you teach calculus, but to somehow figure out a way to turn it around, increase engagement, get it back, get some enthusiasm back that is inevitably lost given what happened. So that's what I'm excited about with the Calculus 3 class, Kappa. That's this time. That's a nice rug. Second EAG. Now, second EAG is not how you say it. It's actually two and dig. It has to do with a video game called Counter-Strike. Did I get that? A second. Has to do with that. No, it has to do with the other one where you're on a team and you have to infiltrate something. Yeah, Rainbow Six. Rainbow Six. Or perhaps it's Battlefield. It could also be Battlefield. Good. Okay. Yes. Okay. Okay. I should have gone with the first instinct. Oh my god. Yeah, it was CS? Okay. Wow. Wow. All right. But actually, what I have to do now, folks. All right, who's here? Hey, second Desert Eagle is here. Wow. Long time. But what I have to do now, I actually can't access my WebAssign, which of course all the calculus classes use it. So I need to call WebAssign and tell them that I am me. And hopefully that means I can see what the heck the class is assigned. I gotta do that. I gotta make some I gotta make some phone calls. So that's gonna be pleasant. It's weird. So what happened? Let me tell you what happened. What happened was, 6 months ago, WebAssign's page looked like this. The WebAssign login looked like this. There was like a box, and then there was like, oh, WebAssign something, and then there was like one box and another box, and it was like user and password. And my computer, I guess, recognizes the screen. Yo, guys, I don't know anything about computers, okay? Ask Crow how this works. But a computer recognizes the screen and would just auto-fill the thing. Boom. Boom, bam. Like, done. Yeah? And I just press enter. Now, what happened is I went back like 2 days ago because I had to, because I'm taking over this class. 2 days ago. This is really exciting, right, folks? You guys are really into this story? 2 days ago, I go back. Now, how do I go back? I go to this. I start typing WebAssign on the top thing, and it just completes it like it used to. I'm not doing anything different. You go to the, the top one? The top thing? And you just start writing, and it you know how it can just like finish it? Because you've been there before? Just finish. Okay, I did the same exact thing on this one. But now it's different. It's like, it's a different size rectangle. And now it says some sen gauge. And it just says one box, which is user. And it's a different color. Like the color scheme changed. It was like red. Like these were all red. And now it's all blue and stuff. Like blue. And I guess my computer doesn't remember because it's different shapes. So I think I know this email. It was an email address, but an old one that I can't access because it's old. It's like at a different institution. I think I know this, but then I go to write the password in the next part. I've tried everything. I don't know it. And then I tried reset password. Are you guys writing this down? People G, please write this down. Reset password. So I clicked that. With the mouse, I clicked on this. Right in the middle. And it said that it sent me a password reset thing to this old account that I can't access anymore. I have to figure this out. Right, Skugget. That's what I suspected it was. Yeah, it just does. It failed to recognize the page up to homotopy. Yes. Exactly, Skugget. You're starting to get it. Yeah. Yeah. That's right. Now, I can't even reset it, because where does it go? It goes to this thing, which is effectively a trash can. Whose lid is locked. I don't know why I drew that, but that's what's going on. So I have to go call WebAssign or Cengage. Thank you, procrastination. Absolutely. Crow? Yeah, Crow, you're absolutely right. When technology and when tech starts getting too advanced, like 5G, that's when you need to bring out the Shungite. Right, Crow? That's why you redeemed it. So here's your Shungite, Crow. May you have a day that's free of technological problems, especially concerning 5G radiation. Here you go. That's what I'm gonna have to do, Kappa. Negotiate. Oh, if you use Chrome, that user password is stored in your profile. I know what that is for sure. You can usually get back at it via settings. Yes, I know those things. Awesome. Wanna be it. Helpful. Wow, you made it. You made it in the credits. Thank you. I'll check that out. No, it's shungite. It's not carbon, dude. It's not. Come on. That's like saying diamonds are just carbon. Come on. Sometimes this chat, man. Please. Okay. What a great community. Thanks for stopping by. We're getting closer and closer to the Galois correspondence, which is the fundamental theorem of Galois theory. After it, we'll have to do a little bit more complicated group theory, building on what we knew from last semester. And then finally we'll understand the proof of the insolvability of the of a general quintic and even a specific quintic polynomial. All right, so that's where we're going. Class? Thanks for spamming the chat. Oh yeah, this person, yeah. I guess I'll scroll through all of this because it was relevant. All right, and class, this is what we did today. 3-part perfect lectures, perfectly executed, as always. Can't wait till we get the stream Discord. I don't think there's enough stuff happening. It's not like, you know, Physics OH has like stuff happening all the time. Like quantum and like this and string theory and all this stuff, you know? What do we have? What do we have going? WebAssign problems? Like issues with WebAssign? 5G radiation tricks? What are our categories? You know? What? Exactly, Vixen. Exactly. Yeah, recorder. Just a channel where people just spam great recorder performances. Homework answers. Yeah, Chegg. Our Chegg. Yeah. Skugget. Yo, add them all together. Welcome, welcome, welcome. You didn't quite make it into the credits because I'm getting the heck out of here. Now let's see, who can I raid? We need to raid someone this time for sure. This time we're gonna raid someone. Add them all together? Yeah, it's a good name. I like it. Now, yo, what is this emote on the screen? Hey, do y'all know what that emote was just now? That is Kappa's emote. Kappa streams. Never forget that. Everyone go follow Kappa. If you subscribe, you get that emote that was just on the screen. Shit. How do you do backwards? This one, you see it right here? Oh. Yeah. Not sure what it is, but it's really cool. All right, who are we gonna raid? NASA? NASA's online. Also, Mikey. You guys like Mikey? You guys want to go see New York City? NASA will shout you out from space. They won't even notice. They won't even notice. Really, Skugget? You think? You think so? Now, okay. Well, we're gonna go to NASA then. We're gonna test that out, like science. All right, we're gonna test it out. Okay, this could be our breakout moment. All right, let's see. Let's see what they say. How am I gonna tell whether they say anything or not? You guys have to check. Because it takes me some time to click the buttons to get on the stream with you. What you say? Math raid. Math raid. All caps. Okay? And you gotta spam it a couple times. You have to trust they will. You can't hear. Yeah, there you go, Vixen. There you go. Ready? I'm gonna click raid now. And then I'll be there in like 5 minutes because it takes me forever to figure out how to get there. Okay, ready? 1, 2, 3. Oh, followers only? Oh. Oh. Oh, what? I'm hosting NASA. What? What?